So now that we've examined how one might do this with just two vectors, it's pretty obvious how we could do this with many vectors at the same time. So if our matrix A is m by m, then what we could do is initially let V be a random matrix that has n columns. Right? We could then say, okay, we want to make these columns mutually orthonormal, so we will compute the QR factorization of this, and we will call this our first iterate. Then, until we converge, we can say let k from 0 to whenever, those are our iterations. What do we do first? We create a temporary vector v equal to A times the matrix vk. Okay, that gives us a push in the right direction. But then we want to make sure that these columns are once again mutually orthonormal. So we will let our next iterate be vk plus 1, which is the result from computing the QR factorization of v. Okay. And then if we want to track what's happening with the eigenvalues, then we may even want to say, let's create a matrix A k plus 1 equal to vk plus 1 Hermitian transpose times A times vk plus 1. And what we would expect is that that would eventually become a diagonal matrix where we can find the eigenvalues associated with these eigenvectors on its diagonal. All right? And now we have a more general subspace iteration.